Well, as Chris mentioned, I am currently on maternity leave, so I first of all would like to thank everyone for putting up with my children in the building over the last month or so while I've been preparing this presentation. And most of all, I'd like to thank my husband, Dr Kemp, for all his support and help with the presentation. Okay, so today I'm going to talk about the Virtual Geophysics Laboratory and how it's contributing to the high-performance computing evolution here at Geoscience Australia. I'm going to show you geophysics, but what I really want you to take away from this talk is where we're going with this high-performance computing and the tools that we're putting into place to improve our science here at Geoscience Australia. Now, the Virtual Geophysics Laboratory was a collaboration between CSIRO, the National Computational Infrastructure at ANU, and Geoscience Australia. I'd like to acknowledge that the funding for it was from NECTA, which is an Australian government project conducted as part of the Super Science Initiative and financed by the Educational Investment Fund. Now, I'm only one person in a very big team for VGL. At Geoscience Australia, we had numerous people driving it, helping test it, helping build codes to put into it and guide where it was going. At the National Computational Infrastructure, Ben Evans and his team have been invaluable in helping us get it together. And at CSIRO, those are the guys that actually built it and coded it. Ryan Fraser, Josh Vogt and Terry Rankin were the key players in that. So what is the problem? So we at Geoscience Australia are trying to build Australia's resource wealth while maintaining our geoscience knowledge and capabilities. So what does that mean? Well, that means that we need to explore smarter, better undercover. And we are involved in the Uncover project by the Academy of Science. But what's key in exploring undercover is geophysics. So the geophysics that we do here at Geoscience Australia is vital to what we want to solving these problems. But the problem is Australia is huge. And we have lots of geophysics data across the nation, and we've got lots of stuff we want to do to it. So how do we do that? So here's an example of some geophysics data. So this is hot off the press, not released yet, the magnetics map of Australia for 2014, which my old team at Geoscience Australia has been putting together, Aki Nakamura and Peter Milligan. It's 80 by 80 metre resolution grid of all of the magnetics that's been collected over the last 50 plus years across Australia. It's only about 8 gigabytes in size, but it has a hell of a lot of cells in there, mind my French. So I'll just show you an example of one of the processes that we're doing to it is the variable reduction to the pole. So this is a really important process for magnetic data because it's actually moving the magnetic anomalies into their correct positions, which is very important for drilling so that a mining company doesn't drill in the wrong spot. Now we could not do a variable reduction to the pole on a PC at Geoscience Australia, so it's being done over at the NCI. And we didn't even have codes that we could use, so the actual code to run this has actually been built by Peter Milligan himself because we didn't have anything else available. Here's another example of what we do here. This is an inversion model, another one hot off the press. This is courtesy of the Geological Survey of South Australia. We're doing some collaboration with them in using some codes that we work on the NCI. This is an inversion model at 10 kilometres depth for showing magnetic susceptibility for the Gawler Craton. Now, if you see faintly, this is the whole of South Australia in this inversion. So the concentration is on the Gawler Craton. So the actual inversion size is 1500 by 1700 kilometres, but it's with a 4 kilometre cell size. So the data that we can actually put into it is 80 by 80 metres, but we're still limited to using a 4 kilometre cell size to actually run this inversion. And that's creating 8 million cells. So this inversion result took about 9 hours to run using 128 CPUs at the NCI. So Australia is huge, we have big data, we have big compute, and we also have complex geophysical scientific workflows that we want to run. And a lot of the time we actually have new codes that are needed. So as you can see, we can no longer do any work on our PCs. We just don't have the storage capability, we don't have the processing power. So I didn't bring my prop, but I was going to hold up my mobile phone. Instead, we're just going to do work on our mobile phones now. So what we're going to do is do work on our mobile phones. We're going to hook straight into the National Computational Infrastructure supercomputer from our mobile phones. So this is the answer to what we're doing. This is the new machine, Ragen. It's got 57,000 computer cores. It's got more than 10 petabytes of research data storage infrastructure for us to use, with a peak performance of 1.2 petaflops. So it's ranked the 38th most powerful computing system in the world. And the big one at the bottom is it's got the capability to run these virtual labs, which I'm going to talk about more. So my talk today, I'm going to talk about the history and evolution of high-performance computing at GA and how it led to us working towards virtual laboratories. And then we're going to talk about what is the Virtual Geophysics Laboratory and what can it do for us at the moment. And then we're going to talk about the future of the Virtual Geophysics Laboratory and other virtual laboratories across Geoscience Australia. So the evolution of HPC and virtual laboratories at GA. Well, it's been around a lot longer than I have at GA, so it's been about 6 years in the making. In 2009, we had the initial testing of geophysical inversion software at the NCI. So Richard Chopping and Nick Williams got some codes, actually, that Nick Williams worked on for his PhD and headed over to the NCI. So we've got the claim to fame that the geophysicists were the first people at GA that were over at the NCI. In 2010, we worked our way towards using it then routinely on the NCI. So we started to use the NCI for our geophysical inversions, so we could now create much bigger large-scale inversions like I showed you just before of South Australia routinely for our projects. But we like to show the NCI as this beautiful machine. This is how we show the NCI, you know, when we're giving public talks. But in reality, this is more what it looks like. So we're looking at, we need to be able to work on the NCI, we need to have medium to advanced programming capabilities, we need to know how to work in a Unix environment, so we need to be able to run our own scripting, we need to know how to edit files and text and ASCII, possibly write our own codes. So it's not as easy as just let's just take our software and chuck it on a supercomputer and run it and we'll be able to do everything in a quarter of the time. Here's a bit of an example. I'll map it out for what we do for a typical geophysical inversion. So this is on the NCI or a PC, but much quicker on the NCI. So what we do is we find and download a data set, so possibly that magnetic map that I showed you earlier, and we'll visualise that data and work out what exactly we want to invert. We'll transform to a regular grid, so we have to work in metres, we can't work in lats and longs in a lot of the work that we do at the moment. We have to crop the data to the area of interest because we don't want to have too much data because we won't be able to run the inversion in the time that we want. We'll reformat that data for processing. We'll upload that data to Ragen and configure and start a job. Then we'll download the results. So this is actually using, in the proprietary packages, I think we use about 4 or 5 proprietary packages to actually just set up the data to then send it over. And then on the NCI, we could use 2 or 3 software packages actually sitting on the NCI to run our inversion. So it's quite a complex process. So the issues with this picture is 1, data accessibility, version controls and size. So there could be numerous versions of the data out there. We've got to make sure we get the most up to date and we know what data we're using. Time. Although it's quick to run on the NCI when we actually get over there, it could take us days to actually get that job set up to run. So that's also a problem. And software. We're forever battling at GA to make sure all our software, our proprietary software is up to date. We've got the latest versions, we've got all the updates, and we have access to all of the latest stuff. So that led us in 2010, or Richard Chopping and a few others, to come up with an idea for a virtual laboratory. So the initial virtual laboratory that was built was called VEGL, the Virtual Exploration Geophysics Laboratory, and a pilot began. So in 2011, development continued, and it was proven that it could be done. A virtual laboratory could be set up and to simplify the workflow. So in November of 2011, a NECTAR proposal was submitted and accepted, and it was concentrating on open source software in a virtual environment. So this is when I came into the scene. So in February of 2012, I was sitting at an ASCGP's conference in Brisbane, and Richard Chopping gave a presentation on VGL. And I was working for a gold mining company at the time as a geophysicist, and I was really excited because it was only a small gold mining company that I worked for, and we had a lot of trouble getting access to data, a lot of trouble getting access to software, to inversions. A lot of the time we used very expensive consultants who we didn't necessarily trust what they were doing to provide us with the results that we needed for our exploration. So this idea that there would be this virtual laboratory that would link the most up-to-date data with codes that we could use to give us up-to-date results was very exciting for industry. So I was pretty excited when I went to that talk. And then funnily enough, in June that year, I found myself working here at Geoscience Australia through various funny happenings. So as soon as I got here, it was a great move. So as soon as I got here, I was like, well, what's this VGL everyone's been talking about? What's going on? And looked up the team, and Leslie Wyborn tucked me under her arm and said, all right, you want to be involved? By this stage, Richard Chopping has left to go and do his PhD. So I became the new VGL queen, and I think Richard Chopping was maybe a queen too. Sorry, move back. So I started working on VGL. So I was lucky. I arrived just at the time when the first version was being released of the new NECTAR-funded VGL, and in 2013 we actually had 3 releases, and 2014, even post-funding, we still convinced CSIRO to help us with minimal money to continue development post our NECTAR funding. So what did VGL do for us? It took us from this, where we've got numerous proprietary packages, mass packages, hardcore data, into something much more simple, where we discover raw data, we select our spatial bounds, we build science from our existing libraries using a scientific workflow, we run a job, we collect and publish the results, all within the Virtual Geophysics Laboratory. So we don't have to jump around from numerous packages now. All in the cloud. Okay? So what is cloud computing? We sit out here on the outside. We have our devices, our phones, our tablets, our desktops or servers or laptops. And cloud computing is applications, platforms and infrastructure that sit somewhere else. And that we don't really need to worry about what they are, what they do. What we use here is our cloud is sitting over at the NCI, but numerous people, when you save your photos from your phone or you use your cloud storage account with your Gmail or whatever, it's sitting over somewhere else. And we're not really concerned about where it is, we're just concerned that we know that it's there and it's safe and it's doing what it is. So this is the whole concept of the VGL and cloud computing, is that we don't have to worry about all of this detail of what's going on in here anymore. We just have to be a user sitting on the outside. So here's a bit of a diagram about what VGL does. So VGL, you're sitting here on a computer or a phone or a tablet, and you search through some data that's available on the web services, find the data that you want, use some sort of processing app to apply to it. Here we'll show a few that we have. This is that we have access to in the virtual laboratory at the moment. And then you compute it in the cloud. So at the moment we compute it using the National Computational Infrastructure Cloud or the NECTAR Research Cloud. But in the future we'll be able to compute it in the commercial Amazon cloud. So what are the key VGL features? So VGL gives us access to pre-competitive geophysical data online, the latest data. Okay, so we don't have to worry about versions, we don't have to save things to our computer, we get the latest data that's uploaded by the various agencies that are associated with that. So for VGL at the moment we have Geoscience Australia geophysics data. We have the Geological Survey of WA have put a lot of their data up there, and CSIRO have put some data up as well. So we're working towards in the future getting more data, but that's what we have access to at the moment. It gives us access to the cloud computing and storage that we wouldn't normally have access to, and it gives us access to geophysical data workflows or apps. And one of the major features is also, because we're all doing it within the one environment, we can capture what we're doing. So we call this provenance, but really we can just think of it as allowing us to be transparent and repeatable in the science that we're doing. So we capture a metadata record which records what we've done, and it's ISO 19115 provenance record is what we call it. Alright, so I've given you a bit of a background about where we've come from and where we're at. Now I'll actually give you a run through of what VGL actually is. So this is the Virtual Geophysics Laboratory. This is the address of it. It's currently open for all for research purposes. So you just need your Gmail account or your OpenID account. I logged in the other day and managed to run it again, even though at home on maternity leave. Just had a play and it worked fine. There's also some help available here. So this is what the Virtual Geophysics Laboratory looks like. So we've got a toolbar at the top that guides us through the various steps in our process. So we've got help, we've got the main portal page, information about the jobs we're submitting, monitoring the jobs, and then you've got a login button. This is just based on Google Maps. Over on the left here, and you can use it like you would Google Maps, so you can zoom in and out and you know, change the perspective and you know, add maps and all sorts of stuff. So anything that you can do in Google, you can pretty much do in here. On the left, we've actually got our layers or our data sets that we've got available. So here we can scroll down, and here I'm just showing you a few of the Geoscience Australia coverages that we've got. So our all of Australia gravity onshore map, our onshore and offshore gravity anomaly map. There's some radiometrics in there, and the magnetic map, not the latest 2014, the 2010 version. So we can actually look at information about those data sets. So those data sets are all remote data services. So they're web coverages or web map services. So and this is based on the AusScope portal, so any data set that's available as a web service, we can throw in here. So the hyperspectral data, anything that we've exported out of Geoscience Australia, and there's a lot of work being done here at Geoscience Australia on making our data into these web services. Okay, so what is the data that we're talking about? So when I talk about data on the VGL, I need to also talk about the research data storage infrastructure that's happening over at the NCR at the moment. There is an estimated more than 3 petabytes of publicly funded geoscience datasets in Australia, and the majority of those are actually held at Geoscience Australia. So this is geoscience, and not just geophysics. This is across the whole agency. Currently, the size of the Australian geophysical data collection on the RDSI is 5.1 terabytes. So that's mostly onshore and offshore seismic data. So our data sets that we actually have on the VGL are only 752 gigabytes of data. And that is composed of, as I said before, GEOS, CSIRO and Geological Survey of Western Australia data. And I also should mention that they're not all just grids as well. We actually have point data up there, we have electromagnetic data up there, so we can actually do work on the point data, not just the raster images, which is important for various processes that we might want to run on the data. So here's an example now, if I've highlighted and loaded the magnetic anomaly map grid for Western Australia. So we can see it here sitting on the map. And we can actually select an area of interest that we want to actually run a compute to. So here we can see that so both the gravity and the magnetics has been loaded, and both of those have been selected. We can actually see how big that data set is. So might only be 1.4 megabytes, but it's 362,000 data points. Or for the magnetics, which is an 80 by 80 metre grid, 36 million data points, 138.3 megabytes. So these are relatively large files when you're talking about transferring them across networks and trying to work with them on your PCs. We can look at the data types and change the data types that we're going to select these data sets in. So the default is NetCDF, because this is an open file format that's a lot easier for us to deal with other open source data sets, other open source software packages that are out there, but we have some proprietary data types in there as well. We can actually change the region that we want. So if we selected it and we decided that we actually wanted to make it a bit smaller or larger, we can actually change these latitude and longitude coordinates to what we wanted. And this just tells us the location and where we're putting it. So what's actually happened? So we've got a user that's sitting somewhere logged into VGL. Then they've got the available data sets. So we've got a registry of the data that's available. And they've selected some data. So they've sent a data request to some data storage somewhere, which eventually will be the RDSI, and said, you know, this is the data that I'm interested in. So it's sent that information, but it hasn't downloaded the data. It hasn't done anything more than just sent a message. So then a second step in the Virtual Geophysics Laboratory is then to build a job. So here we're at the submit the jobs phase now. So here we can see we enter the job details, and this is important for how we record the information about that job or the provenance of the job. We can put in the job description and a job name, information about why we're doing it. We can choose then our compute provider. So at the moment we've got the National Computational Infrastructure, the NCI, and the Nectar Cloud, which is the National E-Research Collaboration Tools and Resources. So in the future, we're going to be able to see the Amazon cloud there as well. So flexibility in what computing resources to utilise. So this is really important as part of the VGL. And then we choose our toolbox or app that we want to use. So here we can see eScript, which is a potential field inversion package that we use. It can do many other things as well. And Underworld, which I'll provide, which is a geodynamic package, which I'll show you some information about that in a second. So the App Store. Initially, with our first version of VEGL, the Virtual Exploration Geophysics Laboratory, we worked on getting the proprietary software, which we use here at Geoscience Australia for all our potential field inversions, which is the University of British Columbia Geophysical Inversion Facility software, or UBC GIF, you'll hear us talk about. But for the second version, we wanted to concentrate on getting it open, working out what software was available that was open, so that we could open it up much more to the community, initially the research community, and then thinking down the track of opening it up to to industry. So these are the open source software packages that we've got available on the VGL at the moment. The first one is a Geoscience Australia package built by Ross Brody, who's sitting in the audience here. It's an airborne electromagnetics inversion package. At Geoscience Australia, we've done a lot of airborne electromagnetic surveys across Australia, and it was decided that none of the codes were accurate enough to invert what we needed to do. So Ross worked on his own. So it's a deterministic gradient-based method. He's got a few different versions, sample by sample or line by line, or a whole survey at a time, a way that he runs it. And this is an example. So this is actually each electromagnetic sounding is then inverted singularly or across the line or as a whole survey. Now what's important here is the codes that Ross has worked have been able to be released via VGL, an open source. Are they yet to be released open source properly, Ross? Next month. But they are available on the VGL now, because the VGL gave us the ability to simplify the way that it was deployed, so that Ross didn't have to worry about providing the maintenance and the assistance needed with releasing an open source software package in the traditional way. And here's some beautiful slides of the electromagnetic data sets that Ian Roach and Costello have published. And this is just showing some of the work in the Western Australian Patterson Ebony M survey. So this is the type of thing that we will be able to get out of the Virtual Geophysics Laboratory in the future. The second app that we have, or toolbox, is eScript Down Under. Now, eScript Down Under is actually developed out of the University of Queensland by a researcher called Lutz Gross. And it's Python-based. It's a Python-based user interface, and it's based on the finite element method. It's been optimised for large-scale data sets, and it does a whole lot of work. A whole lot of finite element modelling is you're capable of doing it in the software, but they've actually created a toolbox within it called Down Under, which is made to do gravity and magnetics and joint inversions. Now, the exciting thing about it is that it's a scalable performance to 8,000 plus processing cores, which is pretty amazing for a geophysical package. It's got an open source license, so we could use it in VGL. And here's some examples of outputs out of eScript Down Under. This is the inversion of a gravity anomaly data, so you can see the gravity data sitting up here, and that's the result, the inversion below. Here is a 100 by 100 kilometre magnetic inversion, gravity and magnetic joint inversion, and we're just showing the magnetic susceptibility variation here. So the third app that's available was developed by the geothermal, was put into the Virtual Geophysics Laboratory by the geothermal team here at Geoscience Australia. So I'm not up to speed with it, but Underworld is a 3D parallel geodynamic modelling framework, and it's being developed in collaboration by Monash University and VPAC. So the best person to go to talk to about Underworld is Alison Kirkby, who's now doing her PhD down in Adelaide. So those are the apps. So we choose an app to run our software in, and then we need to set up how we're actually running that app. So here we choose our data set that we're going to run the process on, and we can actually upload our own input files as well. So if you're actually running some software and you need some control files or separate files that you have customised for your own way you run the process, you have the ability to upload them here. And we've got those data sets sitting there, and then we set up the script that we're going to run. So the Virtual Geophysics Laboratory was built for geoscientists, so scientists, so we had to still keep it flexible. So unfortunately we don't have a nice tick box step go through. We've got what we call a glue script workflow, which has its advantages and disadvantages, but the advantage is we still have access to the code. So we can actually write our own code in the virtual laboratory to run it if we want, okay? Or we can actually grab a template from the left which is already set up with the appropriate details that you want for your inversion to run using some standards, and it will actually generate the code for you. And then you can go in if you want to and edit or tweak what you're doing, or you can just go with your defaults. So it's a balance between an experienced user and a beginner. So what's happened now? So our user's still running the VGL, and they've got their processing script and their small input files uploaded. So that's sitting now. So their script that they're generating VGL has now been uploaded to the cloud storage. And we want to tell the cloud compute now to start the processing. So Cloud Compute will then download all the job data, the script user files that you've uploaded to the cloud storage, and it will then download your big data sets. So it actually hasn't had to access these big data sets yet all the way through. It's just sitting there waiting until you're ready to compute it. So then the Cloud Compute will perform those data processing. upload your result back to the cloud storage, and then we get the result. We can get the result back at VGL. So what's happened? So the results are sitting up in the cloud. So we have our monitor jobs thing where we can actually see the various jobs series that we've run in the past and the various jobs that we've run within that. And this is just an example. So the gravity inversion of northwestern Australia. We can see all the files associated with that inversion. So this is the provenance that we talk about. This is how we can have the transparency and repeatability in the science. We can actually see the output files, the log files from the compute, the actual script that went into the data set, and then possibly a workflow version text, so an information that's sent out from the software. We can actually view those log files as well within VGL, so we don't actually have to download them to look at them. And we can actually submit that job to a ISO 19115 provenance record to save it. So this is our provenance record, which shows the boundary box where we've actually run it, the scripts that we have run, all the information, including information about the actual data set that we used, but not the actual data, because we don't want to have to deal with saving all that data set. We just want an accurate record of the exact data that we used and the boundaries that we used from that. Okay, so that's when from VGL we can see what's the processing status, what were the job input and output files that are sitting in the cloud, and we can choose to register that data into some provenance record. So that's VGL, and that's what VGL can do. Okay, so it does have its limitations, and we've worked through a teething process. You know, at the moment, VGL, we don't have access to huge numbers of PCs that we want to get access to through VGL, because we've still got authentication, teething issues with the NCR and all that sort of stuff. So I was hoping Ben would be in the audience and I could quiz him about that. But we're getting there. So, and the exciting thing now is that we've proved the concept of what can happen and how virtual laboratory can work. So in concept, we can get any data, use any scientific workflow or app, and hook into any commercial or research cloud to run these computes. And at Geoscience Australia, we've got various workflows across the agency that we use. The graduates this year for their group project are actually researching the workflows that we do, scientific workflows that we do across the agency, and trying to compile it into a report so that we can make sense of what we do. This slide just shows some of the open source modelling codes that are available that relate to a lot of the science that we do here at Geoscience Australia. So there's lots of open source apps available already that are ready for us just to plug into a virtual environment. We now have support at the agency for the virtual laboratories from ICTIS. So we have a virtual laboratories program with Stuart Minchin as our sponsor. Wendy So is our program manager, with David Lazinski running the design, and Clinton as our science assurance. And these are the people that you need to talk to across the agency if you're interested in the virtual laboratories, and I'll explain what they are in a sec, so you don't have to all try and understand it, because we have this beautiful slide that David has presented with me. Now, the virtual laboratory life cycle. So we have a lot of virtual laboratories that we're interested in running now at Geoscience Australia. VGL is sitting up here in the released and maintenance stage. Okay, so we have VGL, it's up there and it's working. Viral, which is the virtual hazards impact, hang on, this is where, okay, virtual hazards impact and risk laboratory, which is sitting in community safety and earth monitoring. And that's been pretty exciting. While I've been on maternity leave, everyone's been working away, and this is in testing phase, due for release next month. So that's really exciting. And I'll talk a bit about what that has done to assist us in virtual laboratories across the agency. But to give you an idea of what other sort of scientific workflows across the agency we're working on, if I remember them all, Okay, so VFLE is our virtual laboratory for fluids in the earth. Our VLAM is our virtual laboratory for national earth and marine observations. This is a climate, hydrology and environmental virtual laboratory. This is a virtual earth observations laboratory, or virtual laboratory for earth observations. This is a virtual laboratory for INSAR. This is a virtual topography laboratory, so looking at how we deal with our topography data across Australia. And this is a virtual laboratory for composition and time. So we can see that they're splashed across the Resources Division, Earth Community Safety and Earth Monitoring Division, and the Environmental Geoscience Division. So everyone in the agency, not everyone in the agency, a lot of people in the agency are interested in how we can use virtual laboratories to further our science. So the Virtual Hazards Impact and Risk Laboratory was inspired out of VGL. It's repurposed the VGL code base. So we worked out that there were still some flaws in the way that the VGL was coded initially, and so it's built a more generic implementation of the code, so it's going to be easy just to pick it up and repurpose it across the agency into these new virtual laboratories that we're talking about. It's looking at an online code repository for our apps, so our scientific workflows, so the things like that Ross Brody has developed and other apps across the agency, will be able to easily upload them to a repository, make changes and easily incorporate them into the virtual laboratories. And we've actually improved the provenance service, which is our record that we take to have our transparency and repeatability in the science we've done, to make it easy for us to publish our results. So what are we doing with VGL Mark II? So VGL development hasn't finished. We're going to redeploy VGL with the viral code. So once that's been released and tested fully, we're going to repackage that back into VGL. We're going to update all the data in VGL so that we have all the up-to-date geophysical data sets and hook it into the RDSI over at the NCI. We're going to access the commercial cloud, which is really exciting for me, so that we can then get industry out there using it as well, so that they can help get all these data sets in these clouds to help, uncover the next generation of deposits in Australia. And we want to incorporate more open source and proprietary apps. We also, so at the moment we're looking at open source, but we recognise that there are a lot of commercial software out there that we still would like to be able to have access to, and so we'll work with the with those companies to give them the ability to upload their own proprietary apps with the business model that works for them. So the high performance computing evolution. Virtual laboratories remove the technical barriers needed to perform our science. So we want to make data open and available to all. We want to make the scientific workflows open and available to all. We want to make our scientific results transparent and repeatable, so that we're not inventing the wheel every time. We can keep on building on our science to get to the next level. And mostly virtual laboratories are allowing the geoscience to build Australia's resource wealth while maintaining our geoscience knowledge and capabilities. So thank you very much for listening to my talk. More information can be found at this link, or you can log on to VGL and have a play with it any time you'd like. Thank you very much.